So we're talking about 4.3 first derivative test. Well, it's pretty interesting to see what the first derivative tells us about the actual function f. So I'm going to take a function that I know. So this is f of x is 1 over x. And notice that anytime I draw a tangent line on here, right? Anytime I draw a tangent line on here, what do you notice about the slope of all those tangent lines?
It goes to 0.
So what kind of slope, though?
Oh,
So tangents?
Yes, but negative. I heard it. So who's that? Afsun? Nice. Negative. All those slopes are negative. So we're kind of turning it around and saying, instead of me drawing a function and looking at what the slopes would be like, I'm going to look at the derivative and tell you what the function is going to be like. So what's our derivative here?
One over x squared.
Almost.
Negative 1.
Yes, negative 1 over x squared. So notice the function is always negative, right? Because x squared is always positive. So 1 over x squared is always positive, and then that negative out front will always give me negative slopes. So f prime of x tells us about whether the original function is increasing or decreasing, right? So we're going to use f prime of x to tell us the intervals on which f of x is increasing or decreasing. And we'll always use open intervals, okay? I don't know if the book, I can't remember if the book is, I don't want to just consider the end point to be increasing or decreasing. So I always want open intervals. When I did the homework solutions, did I give you all the chapters, or did I only give you chapter 2 and 3 when I posted homework solutions from the book? You're looking at the homework solutions, right? When you do your homework. You're supposed to be. You look at the homework solutions. Did I give you all of the homework solutions for chapter 4 and 5 as well?
So you just check the number and then you go to the part.
Correct. You are one of the lucky ones who bought the book. A lot of other students don't have the book, so I just posted a quick PDF of homework solutions only.
I think it's everything. It
Okay.
goes back index to you.
Yes, thank you. Yeah, it's just all the odds and it's just the answers, right? On purpose, because, well, I'm only assigning odds. But again, I really want you training yourself how to make sure you know you have everything correct, right? Ma'ab, Chris, Udi, Abraham, everybody awake?
Yeah.
Ma'ab, Udi? Alan, thank you.
Yes, I'm here. I'm sorry, my mic was acting up.
No problem. Udi? Udi, are you there?
Wasn't he asking a question earlier? I don't know. Alright, I won't say anything.
Let's look at another one, because there's another aspect of the first derivative test. So the first aspect of it is to explain where the function is increasing or decreasing based on the sign, SIGN, of the first derivative. So we're going to be doing a sign table. If you remember how horrible that was in pre-cal, where we had to tell if the function was above the x-axis or below the x-axis, and you had the grid and test values and all of that. If you don't remember that from pre-cal, you should, because it happens here.
Yep. Definitely do.
Yep. And so if we look at one other, let's look at a nice simple one, maybe y equals 4 minus x squared. You can definitely see that this function is increasing at first and then decreasing, right? We read left to right in mathematics. So we're following that curve left to right. What's our derivative? What's y prime? Well, it looks like negative 2x, right? Negative 2x you'll see is underground from minus infinity to 0. So that means, negative 2x, not positive 2x, sorry. Duh. Right, negative 2x is a decreasing, right? So I can see that I get a partition of the number line, and I can see my derivative is positive all the way up to 0, and then my derivative is negative after 0, right? And so this is why we call it the first derivative test. I'm plugging values into the derivative, right? Obviously when I plug a negative in, the negative 2 times the negative is going to become positive. And when I plug a positive in, right, it's going to stay negative. So now I see that I have a change in my derivative, a change in the sign of the derivative from positive to negative, or negative to positive means I possibly have a local min or a local max. And it turns out that I have a local max. So when f prime of x changes from positive to negative, and f of c exists, right? Where c is a critical value, of course, right? C comma f of c is a local max. So there's our second aspect or process that we're going to include in our first derivative test. Find where the function is increasing or decreasing, find any local min or local max, right? And local meaning is just, right, it might not be the highest point on the mountain, right? Maybe that's maybe the highest point on the mountain, but this is still the top of a hill, right? We're still going to get a critical value from there. All right, let's write down the step by step. Udi, are you there?
I lost him, Jim.
Okay, here's our step by step. Let's graph the function. Even on your homework and on your test, graph the function. Put it on the page. Okay?
Teacher,
yes.
What would the question look like in this situation?
Complete a first derivative test. We're going to do a bunch of examples, so. right? And I've already assigned 3 for first derivative. Now the section 4.3 has everything combined. Every time you do a first derivative test, you do a second derivative test. Don't do that for me. If I tell you only first derivative test, only do the first derivative test. If I tell you certain aspects of the second derivative test, only do those, because second derivative test not only gives me concavity, right? Is the function concave down or concave up? It also gives me inflection points where it's changing concavity or where I'm turning my wheel if I'm driving on the road. And it tells me local mins or maxes. So second derivative test is just a little bit more complicated. But on the test, I'm going to ask you, just show me intervals of increasing or decreasing, or just find a local min or max, or just find me intervals of concavity, right? So just read the directions. So we're going to graph the function, and then in that aspect, I can already tell right away where the function's increasing or decreasing. Sometimes it's very hard to see it, right? If I get really tricky with the functions, but typically I'm not going to. We want to find f prime of x. I guess the graph should include the domain. We should really notice the domain, because the domain is going to decide on my sign table. Do I have to go all the way to minus infinity and infinity, or is my domain restricted, right? Like if I did a square root of x function, when I did my sign table for square root of x, I would only consider this part of the axis, right? I wouldn't consider the other part of the axis because of the domain, right? So find f prime of x. Really easy. We're not really doing much new here. It's just that the process is horrible. Find the critical values. Create a sign table using a number line labeled with the critical values. Pick test values left of, right of, and in between the criticals. It'll make more sense once I start doing a problem. Label the number line or the sign table with the signs of f prime, right? We're doing a first derivative test, so you're plugging in those test values into the first derivative to find whether the derivative is positive or negative at that point. Conclude about the intervals of f increasing or decreasing. Find the local min or max if they exist. And you really can cheat on this. You can use the original graph as much as you can to know that you're right. And again, so there's no reason to have this particular type of problem ever incorrect. I guess what you could do is get your derivative wrong, but then it should show you you're incorrect once you find the criticals. Yes, Afsun?
Actually, you might have just said this, but for number 8,
Yeah.
I'm gonna use like step 3.
Yeah,
and
so yes, if my function, if my derivative changes signs from positive to negative, then I gotta have and the point exists, I could have a max. If it changes from negative to positive, I could have a min. Yep. All right, let's do a problem. This is 27. So I've got the function f of x equals x times square root of x plus 3. And I want to do a first derivative test here. So in general, for me, that means intervals of increasing or decreasing, local mins or maxes. So we want to get a nice sketch of this. I like to use Desmos. You should be practicing with Desmos and your calculator, because on your test you only have your calculator. So f of x equals x times the square root of x plus 3. So there's my function, and you could see it's already given me a couple of important points on here. That's why Desmos is so much more powerful. It can already see the calculus here. So it sees, right, it clearly sees the left endpoint, clearly sees the low point, right? And I can certainly see, it gives me all x-intercepts, y-intercepts, things like that. So I certainly can see that this has a restricted domain of -3 and on, right? So when I do my sign table, I'm going to restrict my number line, right? Good. Let's find the derivative. So you're not copying me on this, you're doing it yourself. You may get there. Anybody get there? 1? Only have soon? Nahom? Yes? Johan?
Yeah.
Nice. Noah? Nice. Alan? Max? Good. Markins? Nice. Chris? Abraham? Maab? Noel? Jesse?
Yeah.
Got there?
It takes me longer, but I can get the point.
Okay, that's fine. So, next step, find the critical values, right? F prime of x does not exist at x equals -3, right? But it's the end point of my, it's the very end of my domain, so I'm not going to test the left of it, right? And f prime of x equals 0 at x equals -2. I notice that I can plug -2 into the function, right? So notice that f of -2 is what?
0/2.
This is my derivative. I want to plug it into, no, I want to plug it into the original function, right? So it's -2 times, so -2, whoops, -2 times square roots of -2 plus 3. So that's -2 square roots of 1, that's -2. Okay, that's important for me because I think that could be a local min or max now, right? So next step is my number line. I know I have a restricted domain of -3 and to the right, and there should be a hole at -2. So I only have one critical value, right? Yes, -3 is a critical value too, but I don't care too much about left of it because it's not in the domain. So I need to find test values. Anything I want between -3 and -2, right? Anything I want. Look at the graph. Anything I want between -3 and -2 will give me a piece of that curve that's decreasing, right? So -2.5 is fine, and then I'll put a 0 in for my other test value. I don't really need to plug these values into my derivative, but I do know I'm going to get negative for my derivative here and positive for my derivative here. I can certainly plug those in, right? F prime of -2.5 is what? -7.5 plus 6 over 2 times square root of 0.5. And I can already see that that's negative. Right? But I can just look, like I said, I can just look at the graph here and know my original function is decreasing, so my derivative better be negative. Right? I could draw tangent lines on it if I really was confused by it. And certainly f prime of 0 is 6 over 2 square roots of 3. So positive, right? All I care about is the sign, S-I-G-N. All right, I'm ready for my conclusions. Am I right? What's my step-by-step? Let me just make sure. Pick test values, label, yes. So I'm ready for my conclusion. Told you it was boring. Since f prime of x is negative on the interval I from -3 to 2, -2, and again, it's always open intervals for me. F is decreasing on I. Since f prime of x is positive on the interval j from -2 to infinity, f is increasing on j. Yes, Upson.
I thought the I stood for interval, so why are we changing the variable?
I use I for an interval, but then because I have a different interval, I don't want to name it. I can name it I sub 2 or whatever. I call it Johnny. I don't care. Since f prime of x changes signs, yes, Upson.
So should it why is it -2? No, wait, I can't.
Yeah. Remember, it's that critical value that's going to cut up my intervals. The critical values will cut up the intervals. Since f prime of x changes signs from negative to positive, and -2 f of -2, which was what, -2, -2, right, exists, -2, -2 is a local min. And it would be smart for you to double check it to make sure you have it right. Obviously, it is correct, right? And I certainly could plug it in here. -2, -2, and just make sure I get that point on there. Graphing it on your calculator is not as easy, but it's not that difficult. Most of the things I'll give you, you'll be able to label them on there and see it right on the calculator. Like this point, you can easily see on the calculator, right? Nice. Not too bad. It's horrible. It's a lot of writing, and that's the worst part of this section. We'll have just as much writing for the second derivative test, even more. Just as much writing for optimization, even more. So we got to give in. Got to deal with it. Let's do another one. This is number 33. I did also post all my Chapter 4 materials, Chapter 5 materials, and final exam materials. So it's all in the folders there on Blackboard. So you certainly can get started on it. And you'll see in my Chapter 4 problems, I put the derivatives from the Chapter 3 test. So, right? So I get to keep going back to the previous test to double check you on it. So you make sure you go over your previous tests, right, before the next test. And of course, go over all of the tests before the final. So this is f of x equals x squared all over x squared minus 1. And when is priority registration for summer? Do we know? Is there a priority registration for summer, or is it just fall and spring? only fall and spring for priority. Is that right, Noah?
Yeah, I only saw priority registry fall and spring.
Yeah.
Still trying to figure out some.
So that means it's open to everybody once summer opens. So where?
Online said registration opens on April 4th. There's no priority.
Okay, April 4th for the summer. So that is next Monday. I don't know if that means at 12:01 in the morning or someone has to come in at 9 and hit a switch to allow the registration. The school is a little bit technology.
Usually that.
The website is pretty weak. Oh, what? Someone has to hit a switch?
Yeah.
Yeah.
And then it says to 25th for priority deadline on summer.
I'm sorry.
So next month, the 25th. This is the
fall courses.
That's for fall.
Yeah, priority registration April 25th for fall.
For fall. This is for summer. Summer is just a Wild West. It's just open. Anyone who gets it gets it.
And the schedule.
no, that's wrong.
Okay.
You sure?
It's
I'm looking at the website right now. I just copied that off.
Okay. So it's not next Monday. Registration is not next Monday. Thank you.
Can you link that?
Well, the start is, but where it stops being priority is the 25th, is what I meant.
All right. We're all on our own. I think most of you should be able to register next Monday, right? If you have 30 or more credits. And there's not a lot of people taking Calc 2 in the summer, believe me. Not enough crazy people out there to fill up the classes. All right, let's take a look at this. What's our domain here? Nice. Where do we have vertical asymptotes?
So that imagine positive 1.
X equals plus and minus 1, right? Oh, very much related to the domain. Where is my horizontal asymptote? This is all pre-cal stuff, right?
By infinity? Oh,
Yep.
wait, no, hold on. Sorry.
Say it again, Chris?
Is it 0?
Nope.
1?
Yep. The way I taught my students is to look at the ratio of the leading coefficients, right? So if they're of the same power, I get x squared over x squared, so that's 1, right? Or you could do long division. So I get a pretty good picture of this graph to begin with. I also have an intercept of 0, 0. Of course, we have our calculators, so I'm not too worried about this stuff, right? But I know I have vertical asymptotes at -1 and +1. I have a horizontal asymptote at +1. I can already see my graph is down here. And then just by plotting points or looking at my calculator, I can see the rest of the graph is here. So this is going to lead us to some critical values that are called partitions that just simply cut off a piece of the function from another piece of the function. And you could see here and here I would have positive slopes, and then over here and here I'd have a negative slope. So I can see I'm going to have two intervals, one increasing, one decreasing, right? and I'm going to have a single local max, right? It's pretty obvious. So, and this is why I like the graphing. I can do all of this stuff. So in the 1800s, when they didn't have calculators, they were still able to graph things by doing all this calculus, right? All right, derivative.
Professor, I feel like the horizontal asymptote would be 0. I'm seeing some values below 1 on my calculator. I think.
Nope. In between -1 and 1, yes. If you think about it, x squared and x squared are the same number, right? So I'm always going to have a number bigger than 1 if I pick a number bigger than 1, I'm always going to have a number bigger than 1. Right? 5 over 4, 6 over 5, 7 over 6. It's always bigger than 1. Same thing with the negatives because I'm squaring it. So less than -1. So just redraw your graph. Yeah. Good. Let's do our derivative. You're not copying me. You are doing it yourself. Oops. I always do that.
Is it you scrolled up a little bit?
Yes, but you're supposed to do it yourself, not copy.
Yeah, I'm doing myself. I'm just checking. I'm not even gonna answer. I just want to see the question again.
So, the function. Anybody get? Nice. Nice, so critical values. F prime of x does not exist at x equal plus and minus 1. Already knew that. If the function doesn't exist, obviously the derivative can't exist, right, at the same point. And f prime of x equals 0 at x equals 0. And f of 0 is 0, right? So we have a possible local min or max there, depending on if I'm going from positive to negative or negative to positive. Nice number line. My number line, notice that I need -1 to be empty, 0 to be solid, and +1 to be empty. And then I'm doing test values on all of that. So this is my sign table for f prime of x. So I want to test -2, -1/2, +1/2, and +2. I can already tell what the sign of this first derivative is from looking at the original function. I know the original function is increasing on the first two pieces and decreasing on the second two pieces. Of course, I could plug them in as well, but you're calculus students, I know you know how to plug a number in. And I'm ready for my conclusions. How are we doing? It's not bad, right? I mean, it's horrible. I know it's horrible, but it's not difficult. So you just got to really have your notes prepared for this test. There's no reason why you should get something like this wrong. If you're thorough and you're checking with the calculator, you'll know you have your derivative wrong, right? Something will be screwed up when you go through this process if you get the derivative wrong. That's the only thing I can think you would make a mistake on. Or not having this list on your notes. Or not making a conclusion because you just don't feel like doing it. Right?
Okay.
No?
Now, when mapping out the number line, we use the asymptotes and the critical values for like pointers, right?
So the asymptotes showed up here for the first derivative because if you're going to calculate the slope of my skis at one point on the hill, I have to be standing on the hill. If there's a hole in the hill, I'm going to fall through. So the asymptotes show up again in the first derivative. We know the first derivative can't exist. You can't find a slope at a point that doesn't exist. Right? Wasn't that our extra... Did I put an extra credit on your test? No, I was on the other class. I put an extra credit. So conclusion, f prime of x is positive on the interval from -infinity to -1 union -1 to 0. Again, always open intervals. So f is increasing on I.
Closed intervals would be square brackets.
No, so the thing about a square bracket is like if I put a square bracket on that 0, it's saying at 0 you're increasing, but if you're not moving, how are you increasing? So I don't. It's just a personal thing for me. It doesn't make sense to talk about exactly at a point that you're increasing. Right? It should be a range that you're increasing.
Yeah.
Yeah. So no square brackets, right? F prime of x is negative on j from 0 to 1 union 1 to infinity. So f is decreasing on j. F prime of x changes signs from positive to negative at x equals 0, and since f of 0 exists, or f of 0 equals 0 is a real number, same thing, we know 0, 0 is a local max. Done.
This is about the only part that's tricky for me.
Which part is that? The conclusions or what?
Yeah, that's it.
Yeah, but it's going to be it's going to be very similar every time.
Yeah.
So just be
the
a good.
rest of it is just be careful.
Yeah, be a good parrot. Be a good robot. Eat your batteries, right? Just know what to do, and do it. So it usually will take a couple of pages on this type of problem. Go ahead.
A lot of this stuff for 4.3 I take for granted because it's just like properties of the function.
Tedious, yes. And there's writing and reading and arithmetic.
Yeah, but this stuff with number line and inflection and critical values, it's very familiar to me. Very comfortable territory.
Good.
We should do one with E.
Sure. Do you see one you want to do?
Oh, I'd have to look.
$13 looks good. E to the 2x plus e to the minus x. I don't really want to do another one, but...
Okay.
No, I mean, we can start it. It is in your homework, so let's start it. Make sure you do the trig ones, because I'm probably going to put a trig one on your test.
Yes, of course.
So f of x, this is 4.3, number 13. I'm just going to start it. I'm not going to do the whole thing, because it's your homework problem. So f of x equals e to the 2x plus e to the minus x. Is that right? Yeah. I could kind of piece these together without the calculator, right? The way my brain is working is I'm going, okay, e to the 2x looks like this, and e to the minus x looks like this. And so then I'm adding those two things together, right? So, so it looks to me like these these pieces added together are going to just increase it a little bit, and these pieces added together will increase the red a little bit, and the other ones will increase the black a little bit. So I'm going to get something like this. And I'm just adding those two values together, but let's not be careless. I don't care. So y equals e raised to the 2x plus e raised to the negative x. The whole idea, well, like UMD, if you went to University of Maryland in College Park, or even at Baltimore County, they don't allow you calculators. So the whole idea is hopefully you're getting enough skills when you practice with your calculator that you could graph anything without a calculator, right? That's definitely how what the philosophy of them not allowing calculators is about. It's not about punishing you. It's about how you're going to study and learn how to graph things. in calculus, right? And so it's about practice and then thinking about how you could graph it yourself, plotting points, things like that. Now you have a first derivative test. You have all those things from pre-cal. You have now first derivative test to show where the function is going up or going down, and where the mins and maxes are. We're going to have concavity. Notice this thing is concave up the whole time. It's a smile. Positive people smile. So
the second derivative would be
positive.
It would be pretty flat as well.
Yeah, it would be positive. Yeah, it does.
Yeah.
It does really look like a quadratic at this point. So yes, the first derivative is going to look like a line. The second derivative is almost going to look like 0.
Right.
Right. So, but because the function is kind of tricky, you don't really see an mx plus b when you take a first derivative here. But the second derivative will be positive. Okay, concave up, positive people smile. Second derivative is positive. Concave down, right? Second derivative will be negative. That's for Wednesday. Let's find our derivative here. So we want to be able to find that critical value, right? So this one's pretty quick, just a chain rule. 2 times e to the 2x minus e to the minus x, right? Very quick derivative there.
It's usually the beauty of e.
Yeah, we know how to take a derivative of e to the x very quickly. Yep. So you can see I have I probably want to try and simplify this as much as I can. Let me see. I'm just going to improvise a little bit. I don't know what to do. There's my derivative. Remember, I want to get all positive exponents. I want to get a single fraction. I want it to be completely factored. It looks like I'm not going to get a critical value from downstairs, right? E to the x can never be 0. But upstairs I should get a critical value. So f prime of x equals 0 implies 2e to the 3x minus 1 equals 0. So I get 2e to the 3x equals 1, or e to the 3x equals 1/2. And I'm going to take the ln of both sides, right? So I get 3x equals the ln of 1/2, or x equals 1/3 ln of 1/2. And there's my critical value. I can play with that a little bit, right? I can mess around with this just a tiny bit. But it doesn't really change much. Meaning I could put the 1/3 in as an exponent, etc. Right? Who cares?
Sir,
Yes.
for this question, is it important to find the most efficient version of the derivative as it's just a derivative?
Well, it's kind of hard for me to think about. If I leave it in this form, it's kind of hard for me to think about where is the numerator and where is the denominator. And that's why I've been asking you to always give me a single fraction, right? So I guess I could try and factor it first, right? I could take out a factor of e to the minus x there, but that's not as easy for most students to do. I think it's easier to always get an LCD. So even if you set this equal to 0, you still would get the same value. But I want you thinking about, do I have a derivative that doesn't exist, or do I have a derivative that's 0? Do I have a vertical tangent line, or do I have a horizontal tangent line? Right? That's what we've been trying to train you all along with. So clearly you think that there's a local min here, right? So you will have to eventually plug that into your original function, but that's not horrible, right? In fact, let me rewrite this as x equals ln of the cube root of 1/2, right? So I can at least just plug in one value. So f of x sub c is e to the 2 times that plus e to the minus that. And you can see the e and the ln again are gonna cancel each other out here, right? Which is kind of nice.
How did you get 3x?
Ln of e to the right, ln of e to anything is anything because they're inverses. Is that Alan?
Yes.
Do you remember me torturing you with this in this last semester? The inverse properties of the logs.
I remember log torture a lot. I hated log.
Well, what if it's cold at night and your furnace doesn't work? You're not going to hate logs then.
Oh, Professor, your jokes are exactly the same type of my best friend joke. My God.
Not quite a full pun, just 2/3 of it. That's why they stink. PU. Afsoon, question?
I know what we did earlier, but at the last part, x is equal to 1/3 ln to the half. Did we do like the log rule to make it cube?
Exactly, cube. Yeah. So if you remember, we had that property of n times log base b of x is the same as log base b of x to the n. That coefficient comes out. It goes back in as an exponent to the argument. Yeah.
What's the point of I didn't hear you for the last line.
Why did I put that in? Because I knew I could just I would be able to easily solve for this value if my ln was simple as possible. So meaning my next step here is to go e to the ln of cube root of 1/2 all squared. Remember that exponent goes in, plus e to the ln of the reciprocal of the cube root of 1/2. Right? Negative coefficient is a reciprocal on the interior. And now the e and the ln just cancel each other. So I get a cube root of 1/2 quantity squared plus 1 over the cube root of square root of 1/2. So it's just I know, right, from all that pre-cal stuff that I want the e and the ln to cancel with each other. So I'm just trying to hide anything that's getting in the way of an e to the ln. This is pretty damn ugly.
We're gonna flip them around until they're right next to each other and they destroy each other.
Exactly. So this thing is pretty ugly. So I get what? I mean, this is good enough for the point. You know, you're going to get a decimal, but when you go to graph it, it's fine. You can plug it in like this. Anyway, you should do all of that work over. Don't trust me on it. Make sure you do it over when you do this problem for the homework.
That's f of x sub c.
Yeah, that's the.
Okay.
So I know I'm going to get a local min there. I can already see it's going from decreasing to increasing on my graph, and I know the point exists. I'm not sure I have the point right yet, but when I plug it in on Desmos, I'll know for sure.
Yeah.
Yeah. Cool. I don't want to do anything else today. Next class we'll do second derivative test. Friday we'll do optimization. And then the following Monday we're pretty much done with chapter 4. And then we're just going to practice. We're going to practice and we're going to do well on this chapter 4 test, right? This one's going to be make or break for some of us. We want to make sure that we can get a decent grade. And all I need is an increase, okay? So if you've been getting 50s, I want to see something in the 60s or 70s, right? And if I can just keep seeing increase in grades, then I'm thinking you're getting it, right? Now, the piece of this that's important for us is the derivative. That's what we need in Calculus 2. We need to be able to do these derivatives quickly and correctly. And then in Chapter 5, we're going to start to undo derivatives. Okay, we're going to start to do what's called an antiderivative or an integral. And so, and those are the two pieces that are big in Calc 2. So we need Chapter 3 perfect. We need Chapter 5 perfect. We need our trig perfect. We need our pre-cal perfect. And then in Calc 2, we talk about antiderivatives, applications of them, and then when things get really tough, we go to sequences and series to take derivatives of any function, or antiderivatives of any function.
That's summation.
That's right. All that summation notation.
So,
Yes.
is antiderivatives like the most challenging chapter?
Yes. I'll say chapter 8 is the most challenging. That's when we find some function that we find some derivative that we can't turn back into a function. And then this is key for all of the engineers. When you're doing differential equations, you have a bunch of things changing and you want to find out what they originally started as, right? So diffeq is a bunch of derivatives in conjunction with each other, how a ship is changing, how a planet is changing, how the atmosphere is changing.
I was talking to a friend the other day about math, and it turned into a like 40-minute discussion about oh man, it started out as Fourier transforms, and it turned into something else. I'd have to pull it up, but
that's
besides the point.
diffeqs. It's diffeqs. Yeah.
Yeah.
Yep. Differential equations. So, but only the engineers have to take that. Even if you're a computer engineer, you're going to take that. Any computer engineers in here? Computer engineering, I would just recommend taking linear before you take diffeqs. Okay. So we're done. Let me stop my recording. Let me stop my share. Have a great day. I will be around for office hours today if you want to meet. Otherwise, I'll see you Wednesday.